All right, welcome everyone. Let's get session 7 started here. Welcome to everyone. I see some people from all over the world. I wish we were seeing each other in person in Finland, but it's still good to have you here at this virtual session anyways. My name is Kimberly Young. I work with Vireo Advisors, and it's my pleasure to share today's session. So today is on testing approaches of cellulose nanomaterials, and we have 4 presentations that look at testing approaches as it relates to different properties and also in the context of safety. So please, as you're listening to the different presentations, please use the chat box, which is on the left of your screen. You can send questions either directly to me or to the whole group. And hopefully we'll have some time to address all the questions after each speaker's presentation. So before I go forward, I just want to remind you all of TAPI's antitrust policy that states that TAPI is a professional and scientific association organized to further the application of the sciences in the paper and related industries. Its aim is to promote research and education in the areas of interest of its members. TAPI is not intended to and may not play any role in the competitive decisions of its members or their employers, or in any way restrict competition in the paper and related industries. So with that out of the way, let's get going so that we have some time for some questions for our speakers and some discussion. So first up is Ayush Jaiswal, who is a research scientist at VTT Technical Research Center of Finland, where he works in the functional cellulose team. His main expertise lies in the fields of suspension rheology, cellulose film production, coating processes, and fiber-based foams. He is also currently pursuing his doctoral studies at Åbo Academy University in Finland. So let's go to the tape and hear about high consistency enzymatically fibrillated cellulose and their applications.
Hello everyone, my name is Ayush Kumar Jaiswal from VTT Technical Research Center of Finland, and today I'll be talking about tuning properties of high consistency enzymatically fibrillated cellulose termed as HEF-cell, the study for various applications. But before we look into the HEF-cell process, let's look at the enzymatic route towards making nanocelluloses. In the literature, commonly used enzyme cocktails have included endoglucanases, exoglucanases with a combination of hemicellulases. And the major enzymes here, the endoglucanases, their activity is selective to the beta-1,4 glucosidic bonds, and they have been shown to act along the dislocations on fiber surfaces, whereas the exoglucanase activity is on the ends of cellulose chains. So for example, if this is a bundle of fibers, the endoglucanases work towards fiber cutting, and exoglucanases works on the ends towards releasing the cellobiose units. And in this method, enzyme access to the fibers must be ensured, which can be done via bleaching to remove lignin, and for example, by refining, where we increase the total accessible surface area for enzyme activity. And hemicellulases also have been shown to allow better access for enzymes, and that's one reason why hemicellulases can be used to remove partially the leftover hemicelluloses from the source raw material. And each raw material has a different chemical composition, so the enzyme cocktail needs to be altered for different raw materials. So now looking into the HEF-cell process, it's a mechanical enzymatic treatment. So what it means is that we have a source pulp, we dose enzymes into it, and we use a sigma mixer to, as shown in the picture here, to mix the material with enzymes at high consistency. So the processing can be done at consistency above 20%. And in this case, the interfiber friction plays an important role in actually defibrillating the fibers along with the enzymes which are helping for the same way. And later the material is washed, the enzymes are washed away and also deactivated by heating the material. So in this case, the enzyme cocktail has been tailored for wood pulp as a raw material, and the ratio of endo and exoglucanases has been optimized for lower fiber cutting, lower amount of yield losses, and higher degree of fibrillation. And the final material is usually obtained at around 20-25% solid, so rather high consistency material. And in this particular study, we have attempted to study the HEF cell process in more detail to look at the tunability that we can get from this process. So we use 3 wood pulps as a raw material, namely never dried softwood, once dried softwood, and once dried hardwood. And we use 3 different enzyme dosage levels, 6, 8, and 10 milligrams on per gram of dry fiber weight, and to produce 9 different kinds of HEF cell, different grades, and then study their morphology, their carbohydrate composition, and then the resultant water retention and rheological properties. And if we go towards looking at the morphology, we see that on the left is the optical microscopy images. We see that this never dried softwood in the first row. For example, we see good and long fibers in the pulp, typical of softwood fibers. And as we increase the amount of enzyme, we see that these longer fibers start to disappear, and then we have smaller and smaller pieces of fibers left, which clearly show that the enzyme has shown a cutting action. But all of this material that is being fibrillated is not visible by optical microscopy. So if we take basically if we centrifuge the material and take the supernatant and then look at it from the AFM, we see that the nano fraction of the material is seen to be between 5 and up to 20-25 nanometers in diameter. And gravimetrically, this fraction of nano-sized material is around 10 to 20% of the total mass, and rest is then micro-sized fraction. So this material possesses a very wide particle size distribution, and this is rather heterogeneous as compared to conventional nanocelluloses grades like Tempo and MFC, which are more homogeneous. If you look at the carbohydrate composition, the hardwood pulp, as we see, has a higher amount of xylene and lower cellulose, typical of hardwood raw materials. And the key observation here is that, first of all, there were no hemicellulases used in the dosed cocktail. So it's purely a mixture of endo and exoglucanases. So we are talking only about cellulases. And if we see that as we are increasing the enzyme dosage, we are increasing the amount of liberated reducing sugars. That means more material is being lost because it is being dissolved and then washed away. So if we are increasing the enzyme dosage to get more fiber cutting, we have to compromise on the yield losses. And the molar mass reduced from around 700 kilodaltons for all source bulbs to around 200 to 300 kilodaltons for HEF-cell grade, so showing that the molar mass has reduced upon enzymatic action. And now if we look at the corresponding material properties based on the morphology, the first property that we have studied is water retention. It has been studied using the Obo Academy gravimetric water retention method, which is studying the dewatering of the suspension to blotter paper with mild overpressure. So 50 kilopascals of pressure is applied on the sample, and then we see how much water is being lost from the suspension. So it's rather interesting to note that as we increase the enzyme dosage in all cases of source pulp, we see that the water retention improves. That means that less liquid is being lost from the suspension. And this is rather interesting because as we are increasing the enzyme dosage, we are getting more and more fiber cutting. And more and more smaller particles are being created. So our hypothesis behind this behavior is that more wider particle size distribution is being created as the enzyme dosage increases, which creates a dense filter cake during the dewatering process, and hence there is smaller dewatering. And of course, these measurements have been done as a function of concentration. If we increase the concentration of the suspension, we see a lower amount of liquid being lost, which makes sense because there is overall less liquid present in the material itself. So higher enzyme dosage is seen to improve the water retention. And if we look at the rheological behavior, first, if we look at the forward shear ramps, which were measured using the concentric cylinder geometry, with the testing parameters were rather discussed in the literature, so have been adopted from there. We see that the material has quite low viscosity, even at quite high consistency of 10%. If we talk about conventional nanocellulose grades like MFC, this viscosity is apparent at around 1 to 1.5% consistency, which is a special characteristic of the HEF-cell material. And as we can see from this curve, as we are increasing the enzyme dosage, the viscosity of the material is reducing. So the material is becoming more liquid due to higher fiber cutting when we are increasing the amount of enzyme being dosed. And the materials are showing highly shear thinning nature, which is typical for cellulose nanomaterials. And if we look at these curves, so these can be divided into 3 regions. The first is the low shear regime, where we are still seeing shear thinning. Then the viscosity sees a plateau, and then we have another shear thinning regime at higher shear rates. So this behavior is typical for nanocellulose materials. This has been observed for fibrillated materials before, and a hypothesis to explain this behavior of this viscosity plateau at around 10-second inverse is the snowball hypothesis, which basically says that the fibrils, they are flocculated in suspensions, and these flocks themselves start to move at low shear rates, thus having shear thinning behavior. But as the shear rate increases, these flocks, they collide with more materials and they grow in size, and hence creating a resistance to the flow, and they become so big at around this 10-second inverse that we see a viscosity plateau where the shear thinning stops. But after that, the shear rate becomes high enough to break down this soft fibrillar flux, and we start seeing shear thinning again. So this is a probable explanation to the appearance of this kink in the curve. And if we look at this particular work, we did power law fitting on the forward shear rate curves for all the materials, and we see that in the initial low shear regime, the materials has very low power law index. That means a very highly shear thinning nature, and after the plateau, that shear thinning nature is less pronounced. And these curves, when we of course change the concentration of the suspension, the solids content, they directly affect the viscosity of the suspensions, and we try to derive a correlation between the solids content and viscosity. So we found that if we fit the viscosity as concentration to the power m, this parameter, it ranges from roughly cubic to quadratic. So we have very, very strong dependence of viscosity on the solids content of the suspension. And it must be noted that this parameter m here is not unique, but is a function of shear rate, and these values are calculated at 1 second inverse arbitrarily. And it can also be seen that there is more pronounced shear thinning behavior as the consistency increases. And if we look at the viscoelastic properties, which were measured using the vein and cup geometry, the amplitude sweeps were performed to ascertain the linear viscoelastic region, which was at less than 1% strain, and then frequency sweeps were done. we see that there is very little gelling of the suspension. So the gel point consistency is rather high. So these measurements could be made only at 7 and 10% solids. And then we are seeing gelling behavior. But still, the yield stress, even at such high consistency, is rather small, less than 30 pascals. So it makes these materials rather suitable for 3D or screen printing application where high yield stress could be a big challenge. And then if you look at the film formation properties, these films are somewhat transparent, but quite hazy. And if we look at the strength properties of 50 GSM films with no plasticizers, we see that the film density is rather low as compared to films made out of Tempo or other more homogenized MFC grades, where the film density could be around 1400 kilogram per meter cube, where here the film density is rather low due to the presence of rather larger fibers, fibrils in this case. So that reduces the film density. So films are a bit more porous, and that directly correlates to the lower tensile strength. Conventionally, these values could be over 100 megapascals, but here it ranges from around 30 to 50. But still, we have good film formation without any plasticizers. That is being demonstrated here. So now we have studied a lot of properties of this different grade of HEF-cell materials. So how can we make use of them? In here, I'll present a property application map. So if we look at three chosen properties, first applications, first is the films and coatings, second is 3D and screen printing, and third is rheology modifications. So the high consistency of HEF-cell material is useful for all three of these cases. For films and coatings, high consistency is relevant to reduce the drying demand. For 3D and screen printing, high consistency helps with shape fidelity. And for rheology modification, high consistency helps in reducing the total material demand needed to get desired properties. And then the rheological properties, the high solids viscosity of this material and low yield stress along with pseudoplastic behavior like conventional nanocelluloses make them quite suitable for films and coatings and 3D printing, where it's much easier to handle these materials. And this pseudoplasticity is also relevant for rheology modification, where if we have to convert a Newtonian fluid to shear thinning, we could do by addition of such materials, for example, in oil field applications. And this high consistency also helps in efficient logistics of material, energy or water savings, and the rheological properties allow easier pumping and mixing of the material, which are very important for industrial scale handling of these products. So all in all, we see that these high consistency materials, they offer a lot of advantages, and properly characterizing them and studying them and comparing them with conventional materials is needed if we are looking to take nanocellulose forward to industrial scale applications. And also, it's important to note that the HEF-cell process is tunable. It can, by changing the process parameters, we can create materials with different rheological properties, which can be correlated to their morphology in itself. So thank you for your attention. And if there are any questions or comments, I will be glad to answer them. Thank you.
Thank you, Ayush. That was a really interesting presentation. So I remind the audience members that please put your questions into the chat box on the left side of your screen. And right now there aren't any, so let me start. First of all, are we able to get you on the screen here?
Oh, yes.
Yeah. All right, perfect. Hi, Ayush. First, I was just wondering, what was that interesting structure behind you in the presentation?
It was a ball of this high consistency nanocellulose material that we had produced with this enzymatic method.
Ah, that's what I was hoping you'd say.
Just to show, like, as an image, like, it's really
ultra high viscous material, so you can actually just turn it into a ball like that.
Very cool. Very cool. So you mentioned that sometimes you get a wide particle size distribution when you make these materials. And I was just wondering, within one sample, do you ever get like heterogeneity within the sample? And if so, like how do you ensure homogeneity to kind of measure the viscosity or other properties?
Well, this enzymatic process, or at least this Hefsel process, which is basically dosing the enzymes and just mixing the material for a long time, it fundamentally leads to materials with wide fibril size distribution. So there is, I think, of course, as you said, that in small parts of the samples they are non-homogeneous, but as a whole, the material, I mean, of course, we make it batch wise, so each batch has its own properties, but closely controlling the process parameters helps us to maintain those properties. For example, the rheological behavior or the morphology, or basically the ratio of the micro-sized fibers to the nano-sized fibers and so on. They can be controlled with the process parameters, but making them uniform then requires further processing. For example, passing the entire material through a microfluidizer homogenizes the particle size distribution.
Right. Makes sense.
But that requires a bit of dilution. So you cannot pass this material through a homogenizer, let's say at 25%.
Right, right. And then I also wanted to ask about the enzyme. Do you see a dose response with the enzyme in terms of the cutting of the bonds? Like, is it if you double the enzyme, you get double the amount of? Is there some sort of relationship there?
Yes, I think that has to be quantified. We haven't quantified it yet, but we see a clear effect that even if we are increasing or decreasing the enzyme amount, we get very different materials, as you could see from the rheological characterization that I showed, that the viscosity of the material changes drastically. And of course, as we are dosing more enzyme, we are also losing more material in terms of soluble sugars, because when we are washing the material, it just gets washed away. So I think there has to be a sweet spot between how much nano-sized fraction we want and how much yield we can compromise on.
Right. We do have a question from Jeff Notes. Great talk, Ayush. Have you measured the loss modulus of the high consistency films? I can repeat it.
We have not measured the modulus of the film. Well, of course, we have measured the tensile properties. So, of course, these values should not be difficult to find, because we have both the strain and stress values. So, but I think by this loss modulus, I'm not sure what you mean. You mean this Young's modulus for the films, or?
Jeff, if you want to follow up as to what the loss modulus is, please do so. And if not, then maybe you can get in touch with Ayush afterwards directly.
Yeah, of course.
All right.
Happy to answer all questions.
Perfect. Okay, well then, thank you so much, Ayush. Very interesting talk. Thanks for sharing your work with us. And we'll move on to the next presentation.
Yes, thank you.
All right, so next up, we have Gregory Albornoz Palma, who is a chemical engineer working at the University of Concepcion in Chile. He has much experience in the rheology of cellulose nanofibril dispersions. And today he's going to tell us a little more about how morphology and size distribution can affect these properties. Okay, so let's watch his presentation.
Hello, my name is Gregorio Albornoz Palma, and I'm going to present my research about the effect of the morphological characteristic and size distribution on the rheological properties of cellulose nanofibril dispersion. Well, the morphology of cellulose nanofibrils, the rheological characteristic and their dispersion, and the corresponding relationships between them are fundamental for understanding the properties and behavior of this material, and therefore its potential use at an industrial level. The multitude of chemical, enzymatic, and mechanical processes and their combination lead to different CNF morphologies, generating material that can be non-homogeneous. The effect of the site distribution is relevant for many systems, which are difficult to fractionate by size, such as CNF. The effect and contribution of this size distribution is present in the rheological behavior of the dispersion. For this reason, the goal of this research is understanding how the morphological characteristic of the CNF produced by enzymatic treatment and their fractionation by site affect the rheological behavior of the dispersion in the dilute and semi-dilute region, and also understanding the contribution of the different site fraction on the resulting rheological properties and the established relationship between both properties. By way of background, the term on cellulose nanofibers refers to fiber with nanoscale site dimension, whose average lengths are in order of several micrometers. Cellulose nanofibers are high aspirated nano-objects, semi-flexible, that are obtained from the cell wall of good fiber and plant through different mechanical, enzymatic, and/or chemical processes. The different methods for obtaining CNF and their combinations lead to different morphological and surface properties, as well as different rheological behavior. Fibrillation produces a material that can be non-homogeneous, containing fiber, fiber fragment, fine, and fibers. Regarding the rheology of CNF dispersion, it should be noted that regardless of the production condition, of critical concentration, CNF dispersion have the following characteristics: shear thickening behavior, thixotropic behavior, and when the shear rate is reduced to zero, the viscosity of the dispersion increases to its resting value. This is because CNF dispersion are held. When a shear rate is applied to dispersion, the held network breaks and the fibrils begin to flow in flux, whose size decreases with increasing shear rate, leading to the shear thickening behavior. This change in size has an adaptation time, which can be long, as is usually reversible, which lead to a thixotropic behavior. Relevant variables that affect the shear viscosity behavior of CNF dispersion and the type of CNF, meaning their morphology and shear surface, solvent, aspirator, concentration, temperature, and pH, where, for example, the viscosity increases with the intensity of fibrillation and concentration, and it decreases with the increased the temperature and pH. Generally, there are three different regions in viscosity concentration relation. A dilute region at low concentration, where interaction effects are not significant, Newton and viscosity, and concentrated region at high concentration, where the viscosity depends on the shear rate due to entanglement. Here, the effect and concentration is stronger. And a semi-dilute region or semi-concentrated region, where the nano-objects start to entangle and aggregate. This region is determined by aspirator temperature and concentration. Regarding the site distribution on polydispersity system, the effect of the virial expansion is additive, and it follows that the intrinsic viscosity of the dispersion is begin by this equation. In addition, the mixture rule used to calculate the viscosity of mixture from the viscosities of the components is the so-called ideal linear mixture with the introduce of nonlinear terms. Materials and meta. The raw material used for the production of CNF dispersion was bleached hardwood kraft pulp. The production process consisted of enzymatic pretreatment, followed by mechanical refining, and finally high pressure homogenization with 0, 1, 2, 4, 7, 10, and 15 passes. To determine the dynamic viscosity of the different CNF dispersion, a Brookfield viscosimeter with a configuration of double cylinder geometry was used. With this characteristic and measurement condition. Regarding the morphological characteristic of CNF dispersion, the length distribution was determined experimentally using a laser diffraction particle size analyzer, and the width distribution of the CNF was obtained by simple random sampling using micrograph of transmission electron microscopy at different scale. Finally, for the fractionation of the sample, the dispersion were passed through different measures using the Williams Precision Freeness Tester fibrillation system with meshes of 45, 60, 100, 200, and 400. Let's get into the results and discussion. Analyzing the micrograph, we can see that from 0 passes we have nano-object. However, the residual fibers predominate. Additionally, as the number of passes increases, the nanofibrillar yield increases. Quantifying from the micrograph of the different CNF, we can observe that we tend to be smaller and with more homogeneous distribution as the intensity of the mechanical treatment increases. Similarly, we can observe that lead tend to be smaller and with a more homogeneous distribution as the intensity of the mechanical treatment increases. To sum up, we can observe that the average width and length tend to be smaller and with more homogeneous distribution. The standard deviation of the sample decreases. The aspiration or ratio between average length and width tend to increase with increasing intensity of mechanical treatment because the process of fibrillation is more severe lengthways than sidways. Exceptionally, between 7 and 10 passes, the aspirate ratio decreases because of the significant decrease in length rather than in width honor. In relation to the intrinsic viscosity, a rheological parameter, we can see that it tends to increase with the intensity of the applied treatment, except between 7 and 10 passes, showing the same trend as the aspiration. The same happens with the critical concentration. In order to verify the values of aspiration and the parameters involved in the modeling of CNF, is that the Worland chain model was used, which provides a reasonable representation of semi-flexible particles. This model consists of 2 parameters, epsilon associated with flexibility and delta corresponding to the inverse of the aspiration. When the aspiration value and a constant epsilon were used, the predicted intrinsic viscosity values are similar to the experimental values. This allows us to corroborate the aspiration and consider a model independent from the flexibility. Finally, there is a relationship between aspiration and intrinsic viscosity that can be described by this equation. To verify this equation, 5 different CNF with and without enzymatic and chemical pretreatment were used, and we found that the relative errors are less than 4% for all of them. To study the effect generated by the site distribution in the rheological property on each sample in the dilute region, different mass fractions were separated, producing 6 fractions, number 6 being the most fibrillated. The table shows the result obtained, where we can see that as the intensity of the treatment increases, a greater nanofibrillar yield is generated. Characterizing the fraction, we can see the critical concentration, average length and width, and their standard deviation decrease as the fraction is smaller, as expected, while the intrinsic viscosity and aspect ratio increase, except between 7 and 15 passes. Same behavior as for the original sample. When studying the effect of the site distribution on the intrinsic viscosity in the dilute region, we can see that there is a linear relation corresponding to the weighting between the mass fraction and the intrinsic viscosity of the fraction. In relation to the diameter of the sample, the same behavior is observed, where the diameter of the sample is obtained by means of the diameter and mass fractions of each fraction, corroborating this result. In the semi-dilute region, the analysis is complicated because the viscosity of the samples depends on the more factors. To study the contribution of the different parameters of relevance in the viscosity of each sample, a regression analysis was performed with two interactions, obtaining as relevant parameters the concentration, the length, and the aspiration, with a concentration-aspiration interaction and a length-aspiration interaction. This model presents good statistical parameters. In addition, the relevant variables that explain the viscosity of CNF dispersion in the semi-dilute region and related to the viscosity depend variables of polymer solutions, solvent, concentration, entanglement, and molecular weight, where the molecular weight is replaced by the aspiration and the entanglement and substituted by the length of the CNF. Finally, the mixture rule used to calculate the viscosity of the mixture from viscosities of each fraction by site is the so-called ideal linear mixture with added nonlinear terms. The nonlinear terms have three components: the multiplication of the mass fraction of the different fraction by size, which represents the number of possible interactions, the average viscosity between the fractions, and an interaction parameter, which represents the magnitude of the interaction. In the dilute region, where the interactions are not significant, the value of the interaction parameters are zero. In the semi-dilute region, the interaction between fibrils are significant and the aggregate that are formed depend on the site distribution. The interaction parameter is non-zero. From the table, we can see that the interaction parameters are negative, which show the relevance that the size of the fibrils on fiber aggregate between the different fractions have on the viscosity of CNF dispersion, showing high values of the interaction parameter even in highly fibrillated systems as in 7 passes. Conclusions. There is a strong relationship between the intrinsic viscosity of the CNF dispersion and their aspiration, which can be correlated by a power law model. Such model is independent of the flexibility of the CNF. In the dilute region, the behavior of the intrinsic viscosity of the samples is linear. Regarding the degree of fibrillation, the morphology resulting from CNF distribution satisfactorily describes the viscosity of CNF dispersion, which are explained by combined effect of CNF morphology through their fractions. The references used. Thank you for your attention.
Great. Great, and I'll welcome you, Gregory, to join me on the webcam. Hi, thank you so much for the presentation. That was great. I learned a little more about rheology there. So I'm just going to start off with a really probably silly question because I'm a biologist. Could you just explain a little more about what you meant by the different regions and what's a dilute region versus the concentrated ones? Is that within one sample or is that along a fibril? How does that work? Oh, so when you said what's the difference between what does a dilute region mean?
In the dilute region are not flows, and any specific. In the semi-dilute region are flow. The entanglement, there are entanglement.
Okay, so it's about how entangled kind of the cellulose fibrils are. Great. So we have a question from the audience from James Eade. Hi, Gregory, great talk. So given the complexity of measuring the cellulose nanofibril length, I'm curious which method approach you took to characterize the lengths of your different grades of CNF. So what method did you use to measure the length of the CNFs?
Okay, to measure the length of the CNF, the laser diffraction particle size analyzer equipment. The simple laser diffraction size analyzer equipment measures the length of the sphere of equipment volume, but it's capable of quantifying irregular chains. It's very similar of the static light scattering, but it's not the same.
Okay, so it can measure. So then, is it measuring the agglomerated cellulose, or is it measuring the fibers themselves?
The fibers. One fiber.
Fantastic. Great.
But depend of the region of the concentration, because the dilute concentration, but I don't entangle, is only fiber, but in semi-dilute region is flat.
Oh, okay. Okay, I understand. Yes. So it's probably a little more accurate when you have more dilute concentrations.
For this important that the concentration in the sample.
Okay, great. So I'm understanding that the aspect ratio, you related that to viscosity, and then then is there a relationship between the aspect ratio and the fibrillation state of the material?
Yes, the increases of the fibrillation is the aspect ratio increases.
Right, great. And we have a question from Estavo Mai. Hi, Gregory. Could you comment a bit more about how you calculate intrinsic viscosity?
The intrinsic viscosity measured with a low concentration at a low concentration with the sample at a Newtonian behavior. The viscosity specific versus concentration at the linear behavior. At the zero concentration, the intrinsic viscosity is the value.
Great, thank you. And just one more question: where did you find the worm lake chain model? Is that something you came up with, or is that something that's used for other fibers? Yeah, where's the model from?
The worm chain model is the other author is semi-flexible. We use other model, rigid model, but the experimental value is no predicted specific the data experimental, but the flexible model is very good for a specific this material, because the nanocellulose nanofiber is a flexible nanomaterials. The semi-flexible nanomaterial is a good model and not specific with this material, but is good for nanomaterials.
Great. Thank you for clarifying that. Well, thank you so much, Gregory. It was great to hear about your work, and we appreciate you joining us today.
Thank you.
Okay, so we're going to move on to the next presentation, which is it's my presentation, so I get to watch myself on the screen. Yes, I'm with Vireo Advisors. I'm a toxicologist, and I work in nanoparticle and emerging material research. I do a lot of protocol development, in vivo and in vitro work, and work on safety and regulatory issues. So today I'm going to tell you a little more about the safety testing methods and things we've learned. Thanks. We at Vireo Advisors have been working with a lot of you in industry and with researchers in the area on safety testing methods for novel cellulose nanomaterials. And we want to share a little bit about what we've learned over time about these different methods and approaches. So first, I want to start to talk a little bit about safety and why it's important. It's not just a regulatory requirement. There are a lot of different stakeholders who require safety data. Your customers, for example, will likely require these data in order to apply for their own authorizations and also ensuring that their products are safe. Investors may be interested in these data. You, of course, want to make sure that your employees are safe. And once a product goes onto the market, you will get some scrutiny from the general public and and consumers, who you also want to make sure are appropriately and safely using your products. So nanomaterials have recently been in the spotlight. Of course, we know that a lot of different products are being more commercially available that contain nanomaterials. And we do know that there's been some increased regulatory scrutiny. So even though we know that the bulk form of cellulose is exempt or authorized for a lot of different applications, we are finding that a lot of regulators are requiring more data, or at least a review of the novel or nanoforms of cellulose. And we know for other nanomaterials, regulators have actually gone back to do re-reviews of products that have already been on the market for a while. So for example, the European Food Safety Authority, EFSA, re-reviewed titanium dioxide particles, which were deemed to meet the definition of a nanomaterial. And over a concern for potential genotoxicity, the EFSA experts have now said they no longer consider titanium dioxide safe when used as a food additive, and this may lead to its removal on the market. We also know that there's increased scrutiny because there is a legal requirement now to label some of your products with nano. And also a number of academic papers are increasing, especially on cellulose nanomaterials, and to show, and we do know that there is a bias towards publishing of toxicity studies that do demonstrate adverse effects. And when you submit your regulatory dossiers, you need to include all these publicly available data. We also know that media reports and advocacy groups are bringing attention to nanomaterials. For example, hydroxyapatite nanomaterials, which are just made of the same materials in human bone and teeth enamel, has actually received a lot of headlines. And things like headlines touting needle-like nanomaterials or needle nanomaterials in baby formula have really caused a lot of public outcry. And so even though that these are different materials, the risk of any sort of bad publicity for any nanomaterial affects all producers, because sometimes the public can't differentiate between different types of nanomaterials. And so you fall under the risk of being grouped with riskier materials. So what you really want to do is make sure you demonstrate the safety of your nanomaterial. You collect those data prior to going to market, so that when you get reviewed by the public or regulatory agencies, you aren't faced with any uncertainties about the safety. Now, with that in mind, you want to develop a safety testing plan, and you want to consider things like your stakeholder needs, your regulatory needs, information that you may need in order to ensure quality control of your product, what kind of information you want to provide as part of your marketing, and also thinking about future risks and potential liability. So how could your products be used? How could they be misused? What's going to happen to them after they get disposed, and so forth. Also, something that's being echoed more and more is to use realistic scenarios when you're testing your products, for example, using realistic doses and exposure scenarios, which isn't always captured with standardized testing. So there are a number of standards and guidance available. Of course, there's standard testing methods. Some of these methods may need some slight modifications, which is usually allowed, but you need to provide justification. You may also want to consider doing your tests under with labs that perform good laboratory practice or accredited under good laboratory practice, which ensures that there are some rigorous methodological standards and record keeping within that lab and doing that test. And this is required for most regulatory submissions. Also, we can look to the EU for some guidance on nanospecific testing. Both EFSA and the Chemicals Agency have released nanospecific guidance, and they provide advisory notes on testing, sample preparation, data quality analysis, and reporting, which can be really helpful for cellulose nanomaterials. And we've incorporated some of those advisory notes into this presentation. And also, we can take a look to this review paper that we wrote with many of the members of TAPI Nano. And one of the chapters is about appropriate safety testing methods for cellulose nanomaterials. So if you have your testing plan and you're moving forward with testing, there are some considerations. One, ensuring that your tests are appropriate, they represent the right exposure route, they are the tests you need for regulatory approval. Are they validated? Are they standard methods that are widely accepted? If not, you may need to validate your methods and prior to submitting to regulatory agencies. If it's not a validated method, then you may be able to still use it. You probably will still be able to use it as a supporting data, but maybe not as the main piece of data that you can use to rely on to show safety. Can the test be used in multiple jurisdictions? There are some methods that are specific to specific agencies. Do the tests involve animal use? Most agencies are trying to move away or use animal testing as a last resort. And some, such as the EU, require that you first submit your testing plan in order prior to doing animal testing. I also want to highlight this new transparency regulation in the EU that recently came into force. Any tests that are going to be submitted as part of a dossier to the European Food Safety Authority have to actually be notified prior to starting the tests. So you will get penalized if you don't notify and then you submit a dossier with tests that you did not notify. And of course, considering whether or not your methods have any nanomaterial or cellulose specific considerations. So this is just to demonstrate kind of the different applications you could use and thinking about different exposure pathways. So of course, occupational with a dry material, you may be concerned about the inhalation and the potential environmental effects if they're ending up in the soil or water. And there's a wide range of safety studies that can be performed. These are some of the basic tests that are often required for regulatory requirements. So things like genotoxicity testing, dermal and eye testing, for example, personal care products. A lot of these are actually, you can use validated in vitro tests for these types of testing. For other exposure routes, you may need to do acute or subchronic testing in vivo, and also add on a toxicokinetic test, which actually looks at where the cellulose nanomaterials may be going in the body, seeing if it's crossing any barriers that are unexpected, or if it's ending up in any organs other than those that you're targeting. You may be able to use some simulated tests to do these types of testing. If there are any effects found in these kind of basic tests, you may have to do kind of more extensive testing, such as reproductive testing. And I also want to quickly highlight some read-across tests. So these are tests that can provide some supporting data, or you can kind of more easily do in vitro on multiple forms of your material. So you can do cell viability or oxidative testing, immunotoxicity, or look at membrane integrity. And of course, if your product is going to end up in large amounts in the soil or water or in the environment, there are a number of different endpoints you can look at. Now, I just want to quickly talk about a couple tests that may not be valid for cellulose nanomaterials. These are standard tests that may get recommended by non-nano specialists, but we know that the bacterial assay or the Ames assay, which is a genotox assay, is not appropriate for nanomaterials because they can't cross the membrane of the bacteria, or they may have antibacterial properties that may just kill the bacteria. And also, there are certain tests where the nanomaterials settle too much and actually cause like mechanical binding to the organisms as opposed to kind of physiological effects. So things like the Daphnia invertebrate tests may not be appropriate for things like cellulose nanomaterials. I just want to quickly touch upon some types of read-across data and supporting tests. James is going to talk about these more in the next presentation, but EFSA guidance does provide some ideas on how to do some realistic testing. So this would be nanomaterials that go through gastrointestinal digestion, a simulated digestion, and then you take the digested cellulose and you actually do some in vitro tests in cells and also looking for oxidative stress or inflammatory markers. And you can read more about this. Both CNCs and CNFs have gone through this process in these two papers here. And EFSA has the guidance on how to perform these tests. So I want to talk a little bit about methodological considerations. So when you're actually choosing your tests, you of course want to use appropriate concentrations. You may also want to do control groups with other celluloses. I say this because, for example, in dietary testing, we know that dietary fibers, including conventional cellulose, can affect some physiological parameters such as triglyceride levels. And so if you only test your nanoform of cellulose and you find physiological effects, you find effects in your testing, you don't know if that's attributed to the fact that it's a smaller form or if it's just something that all celluloses would affect. Also, you want to think about realistic delivery methods. Again, for oral delivery, you can consider gavage or mixing it directly into the feed. Specifically for cellulose nanomaterials, since they're rheology modifiers, we do know viscosity can be a challenge. So if you want to gavage an animal with higher concentrations, it can be a challenge to get through the tube. Also, because the materials are all gelled together, they may not be quite as realistic because they don't go through the, for example, mechanical chewing and mixing with the food, kind of skips a couple of the steps. However, there are pros and cons for different types of delivery there. You also want to make sure that your sample is prepared consistently, especially if you're going to be using it across a number of different studies. And if you're going to be doing things like repeat dose testing, where you want to make sure that you're giving the same dose to the organisms every day or at every feeding. It will be a regulatory requirement to show that the cellulose nanomaterials are uniformly dispersed throughout the food or the media that you're delivering. Another way to kind of consider the quality of a study, either whether you are interpreting it or whether you're publishing something, is to use quality criteria. I just want to quickly highlight some of the work done by Krug and Wick, which is still applicable. And this helps you kind of interpret a study. So a study, for example, could be clearly marked as overload or non-overload. So whether or not they are realistic doses or doses that are really high in order to specifically look for the mechanism of effects. This helps interpretation, really helps interpretation of a study. Studies should contain data on the dose-effect relationship. Do the studies look at the potential interference of nanomaterials, especially if they're doing things like biochemical testing, because we know nanomaterials can bind to dyes or affect fluorescence or absorbance. Looking at whether or not there are other contaminants or solvents that could be the reason for observed toxicity. Are the test conditions realistic, and do tests have controls? James and others did do a risk analysis of a number of inhalation studies on cellulose nanomaterials, and you can see how these criteria can be applied to a study for interpretation. The last thing I want to touch on is the importance of detection. This is one of the biggest challenges for cellulose nanomaterials. We know that we will need it for things like measuring stability, presence, and concentration in food and feed and media, in order to make sure that you have the right doses and to make sure it doesn't change over time. And also to track the nanomaterials in an organism or in media, for example, for toxicokinetic studies. So a lot of conventional methods are not appropriate for cellulose nanomaterials. They're not quite as easy as something like a metal. But we know there are a number of different methods that can be used. Electron microscopy and other microscopy methods are often used by different groups, but can be really time consuming. A simple mass balance can be performed. However, of course, this doesn't detect whether or not this is the nano form of the material. Two things that I wanted to highlight are methods that we have attempted. So there is a validated food and feed detection method of dietary fibers, including cellulose. And this method uses enzymes or acid detergent solutions to kind of break down the components of a feed, and it leaves the cellulose, which is then measured gravimetrically. Unfortunately, this method didn't work that well for us because we weren't able to get fine enough sensitivity, but may be useful for other purposes. So we wanted to put it here for others to use and try. And it is, again, a validated method. One of the methods that we used that worked well, that can be found in this paper here, was the glucose anthrone assay. So it's a biochemical method. It has been validated for linearity, precision, and accuracy. And basically, the cellulose gets hydrolyzed down to glucose, and then you mix this with an anthrone, and you measure the intensity of the color. So we found this actually had really good sensitivity for our purposes, and we were able to use it. A couple of things I want to touch on are just labeling of materials. So you may need to label materials in order to be able to detect them in the body or in food and feed. And the challenge, of course, is to find a label that is stable in different conditions, but does not affect its physical chemical properties, nor its toxicity. And of course, it's detectable. So fluorescent labeling, has low inherent toxicity, has a lot of different options, and is feasible in biological fluids and tissue. Radio labeling is a standard for toxicokinetic testing, so looking for the cellulose in the body. And most commercial labs are equipped to do this type of testing, whereas most commercial labs are not equipped for fluorescent testing. However, the challenge is to find other labs to work with the materials in order to characterize them properly, as most commercial labs can't work with cellulose nanomaterials and do that characterization. So I want to point you quickly here to a couple of our collaborators and our work that we've done, particularly this from Doug Fox's lab. This is a new paper that demonstrates the use of a tailor-made Bo-Dippy fluorescent probe labeled on CNF. And this was in preparation for digestion studies. And this is a label that is stable and it could survive through the digestive process. So different temperatures, different enzymes, different pHs. Was also tested in a zebrafish embryo system. And in the next conference, I hope to be able to talk more about the studies that we have ongoing for food contact material migration with Texas Red labeled CNF, and also some toxicokinetic studies with radio labeled CNF. With that, I would like to acknowledge a number of different groups, P3 Nano, of course, for ongoing support and funding for a lot of these projects, the industrial partners who contribute their materials and time and money for these types of work. And of course, all of the research and academic partners who do a lot of the lab testing and development of these processes. And of course, the Vireo team. Please do get in touch with us if you are interested in joining our team. It's really dynamic and we have a lot of really interesting questions to work with. And with that, all right. So, it's hard watching yourself, but welcome back, everyone. And I have one question from Yulia that I'd be happy to answer. So Yulia says, realistic scenarios refer to exposure assessment, whereas the testing methods that I am describing in this talk refer to hazard assessment. So how do I think that realistic doses could be included in the test without compromising the detection of hazards? Yulia, that's a really great point. And I think I completely agree that there's a place for both realistic and non-realistic, so higher dose testing. Ideally, in one study, you'd be able to do like a dose response. So you'd be able to do from low to high. So you get to see at what point maybe where you may get an overdose, or you may get an amount of material that's wouldn't be considered realistic, and see what kind of hazards could come from that. However, I think the most important thing, and the reason that I talked a little bit about the study criteria and how to kind of interpret a study, is to kind of highlight whether or not it is considered an overdose, or it's considered a realistic experiment in terms of dosing. And that also comes with how the material is delivered. So is it delivered in a pristine form that hasn't been like mixed in with food prior to being delivered? Has it had a chance to create some sort of like protein corona and bind to other things before it goes into the body? So yeah, I think there's different studies have different fits for purpose. So it could be for hazard assessment, or it could be for regulatory work. So yeah, I think there's a place for all the kinds of studies. But with that, I think I will close this session, and hope that everyone enjoys the rest of the conference. Thank you so much.